Let's do a first example. Engineering researchers compared human real-time scheduling in a processing environment to an automated approach that utilizes computerized robots and sensing devices. The experiment consisted of 8 simulated scheduling problems, and the same task was performed by both human schedulers and an automated system. Performance was measured by throughput rate, or the number of good jobs produced weighted by product quality. Let's say we want a 95% confidence interval for the difference in mean throughput from human schedulers to automated schedulers. Okay, so here we're going to call population 1 the group of humans and population 2 the group of robots. And let's say that we collected a sample of 8 tasks, okay, for both humans and robots. Okay, so here's our output, humans and robots, okay, for these 8 different tasks. And the tasks don't differ, okay? We are measuring the way humans perform this thing and the way robots perform this thing, okay? These two are intrinsically tied to each other because they're looking at the exact same task, okay? So these two populations are dependent on each other, okay? This is not a before and after kind of situation. We can kind of think of it that way, but this is not like the before and after example that I was describing earlier, but still we have the same situation where the members of the population both rely on each other, okay? And so we need to find first the differences between this human output and the robot output, okay? So 185.4 minus 180.4 is 5. 146.3 minus 248.5 is negative 102.2, and so on. Okay, so we've got 8 differences. And we want to find what's the average difference. Average difference is the average of the differences, d bar. Okay, so if we add those up, divide by 8, we should get negative 32.56. Okay, so let's just think about this point estimate for a second. What is this point estimate telling us? Just from a point estimate standpoint only. The average, the sample average, is negative. So what does that mean? Okay, so that should tell us something. If the sample average is negative, that must mean from this sample, the differences on average are negative. That must mean that when we take this number and subtract off this number, on average, we're getting a negative number. That must mean that this number, on average, is smaller than this one, okay? Then we're just talking about the sample here, but that should tell us that throughput for humans must be less than throughput for robots, at least based on our sample, on average, okay? And we're seeing that, right? This is the throughput for the human task. This is the throughput for the robot task. They're quite a bit different from each other. That's because the throughput was higher for robots in this particular task, okay? And we're seeing a lot of negative numbers over here. So on average, based on this set of 8 sample tasks, we're seeing that robots produce a higher throughput than humans, okay? And what was the standard deviation? Well, the standard deviation is actually kind of big, okay? It's 35.03 throughput units, okay? So we have a fairly high variability given this average. Okay, and why is that? Well, we have a fairly large negative number here, 2 positive numbers. That's producing a somewhat high variability. Okay, now let's say we wanted a 95% confidence interval for this difference. Okay, so we're not trusting this point estimate. We want a confidence interval within which we think the true population mu sub d lies. Okay, we think mu sub d lies in between these bounds with 95% confidence. Okay, that means that alpha is 0.05. So what is our equation for the confidence interval? It's d bar plus and minus t for our degrees of freedom, alpha over 2 times s sub d over root n. Okay, degrees of freedom, just n minus 1. That's 8 minus 1, or 7. Okay, alpha over 2, 0.025. So we could go to a t table, go down to the row associated with degrees of freedom 7, over to 0.025 in the upper tail, and we would get a value of 2.365. Okay? So this number is going to be 2.365. We've got our d bar here, negative 32.56. Add to that, subtract from it, 2.365 times s sub d, 35.03, divided by root 8. Okay, that's just arithmetic. If we work that out, we get negative 61.85 up to negative 3.27 throughput units. Okay, and that's with 95% confidence. So I think the true difference between these two populations, the human schedulers and the robotic automated schedulers, they produce the difference in throughput from humans to robots lies in here somewhere between negative 61.85 and negative 3.27 with 95% confidence. Okay, both those bounds are negative. What does that suggest? That suggests with 95% confidence that robots outproduce humans with respect to this throughput measure. Okay? If we take humans minus robots gives us a negative number for both bounds. That must mean that this number is higher. The robots number must be higher to get us this negative number with 95% confidence. Okay? That must mean that robots are producing at a higher rate relative to humans for this throughput measure with 95% confidence.